Welcome back everyone, I'm Rice Ball and today we're going to be tackling part 2 of our material testing for our FPV ducts. I'm here in... Oh wait, I'm in the wrong place, wait. Hey, there we go, that's better. Yes, if you guys have noticed, that intro shot was filmed while I was in the US. Last September. It's been a few months since part 1, but hey, here we are now. With seemingly a different room layout, but just don't ask. Before we go to the main content of this video, let's kind of have a recap of the ducts and the findings that we got in part 1. As always though, there are timestamps, so feel free to skip some parts as there are a lot of yapping in this video. Based on the last video, which was mostly centered on rigidity, PLA ranked first in both axial or squish and tangential bending or flippy-floppy bending. However, it has two downsides. First, it is relatively heavy compared to the other ducts, and second, it is too brittle and will likely fail earlier than the other ducts. However, it is the easiest to print, which can be a huge deal breaker for the other materials. ABS and ASA share very similar characteristics, with ABS slightly performing better than ASA in both rigidity and weight. These are honestly currently my hypothesized, well, very fancy, best materials to use as ducts out of the roster that we have right now, given their availability, ease of printing, and their performance in the first part of this series. Though polycarbonate was a little heavy and kind of ranked 5th in the tangential bending test, I'd say this is still a good option if you want something that can tank a crash. Similarly, PETG didn't necessarily have the best results in part 1, but if you're looking for an alternative to polycarbonate, because of how strong these layer lines are to each other, PETG is also a good option. HPPA12, or a variant of nylon, came as the lightest printed frame, but it's probably not accessible to most people as it's not printed through the conventional FDM printing, but through MJF, which is multi-jet fusion. Really cool technology that's also being used in 3D printer parts, but not something that is commercially available. Which is actually why I'd like to thank PCBWay. PCBWay made these ducts for me, and they do have some events planned for Christmas and New Year's that I think some of you might enjoy. If you guys want to try out their 3D printing services and other things that they have, it's honestly as easy as dropping your STL file and choosing the material that you want. Lastly, the two injection molded frames that we talked about were the Mobula 7V2 and the Mobula 7V4 frames. I wanted to test these out since they were the most common 75 frames on the market during the making of part 1 of material testing. The V2 actually came in the first for weight, but seemed to be really flexible. The V4 on the other hand is heavier, but had better results in axial and tangential bending. To address some things, I did want to add the new Air 75 frame, but I honestly remembered it too late when I finished recording the tests, so I apologize for that. I also wanted to try out the new carbon fiber nylon ducts that Spezi Lover sent to me for our new Hachidorii XS and Spezilicious 65 RST frames, but since the geometry is different, I thought the results might be skewed, so I didn't include these in this video. Now, part 1 was mostly talking about rigidity and weight, but in all honesty, part 2 made me rethink if rigidity even had any importance. You guys did actually point this out in the comment section for the first video, but I wanted to see it for myself. Before we talk about why that's the case though, let's discuss how we'll be doing our crash testing. For our experiment, we're just looking at how these ducts crash and fail. But because of the nature of this topic, I'd like to bring in energy and how energy is transferred. Now, there might be some high school physics involved here, but I'll try to make it as simple as possible. So let's start with kinetic energy. Kinetic energy is equal to the 1/2 of the mass times its velocity raised to 2. So here we have two variables, mass and velocity. Because I just want to see the effect of the different duct materials and their weights, I'll just try to keep velocity relatively constant. In an ideal scenario, most or all of the kinetic energy should be absorbed and dampened by the ducts to prevent parts like motors and electronics from being damaged. I also want to mention the law of conservation of energy, where energy cannot disappear or be created. It's just transferred from one medium to another, or in our case, the forward motion of the drone being transferred into plastic deformation or flex on our ducts. Measuring our mass is simple. We can just weigh our setup, which is my Hachidorii V2 build that is currently using RCN Power 0802 27,000 kV motors running with GemFan 40mm props with 300mAh Tattoo 1S batteries. The flight controller that I am using is an old Happy Model Diamond F4, and it's using an old generic analog camera that I honestly don't know where it came from. I went with this old setup since I know my Hachidorii V2 is about to kick the bucket, so might as well use it for our experiment. Where did I throw that? It just disappeared. I didn't throw that far, didn't I? On the other hand, we also need to measure velocity. And since I don't have GPS on the drone that I just threw away, we'll just need to rely on the fact that we can calculate velocity by dividing distance with time. I'll be recording my normal footage in 30 frames per second, which means I can convert the number of frames into time. So here I've put my video into DaVinci Resolve and it's set to 30 frames per second, and by counting the amount of frames it takes the drone to go from point A to point B, we can calculate the time that it takes to travel 1 meter. For distance, I'll actually be doing something that Mythbusters do in their experiments, and I'll be putting up some boards that have markings on them. I'll be putting some lines at an interval of 50 centimeters, and I'll check how many frames it takes to reach one end of the line to the other end of the line. So this is our setup. These are the boards with the 50 cm increments, which will help us find the distance for our kinematic energy equation. I'm just putting two side by side so that we have a good amount of runway distance, and I just chose the white side since it's gonna help us illuminate the setup for our slow motion shots. Speaking of slow motion shots, just to make things easier for us, I did use a piece of wood as our target board. If you're wondering where I got this, be quiet, I stole this from my sister's room. It is actually her closet's door. So if you're listening to this, ate, I'll put it back, I promise. Speaking of our board, this is made out of 1/2 inch thick wood, and it's backed up by some PVC and some weights just to help it stay stable whenever a drone is crashing into it. As for our cameras, we do have two here in our setup. The first is this Runcam Thumb Pro, which is recording our distance or our velocity of our drone as it impacts the board. To record the impact of our board, we do have our phone here recording in slow motion, and both of these are connected to my laptop over here, which makes starting and ending each recording relatively easy. Plus, since I am far away from the experiment setup itself, I'll be here on my bed, I'll be relatively safe, so you guys don't have to worry about pieces of plastic going into my eyeballs. That is a very vivid description, but yeah, that is basically the reason why we want to be safe. And lastly, we also have this little board right here, which is going to show our test number and the material that we'll be testing. And yeah, hopefully that makes everything easier for me to edit because there is a lot of footage to go through. The plan is to have one battery per trial, but take anywhere from 3 to 5 tries of crashing into the target board in this one trial. I'm going to use this method for the sake of consistency, since battery performance is more constant at the higher end of its operating voltage compared to when the battery is drained. This is also because sometimes I feel like I wasn't consistent, or sometimes I missed the target because I'm such a noob pilot. I'll be putting all my data in this Google Sheet, which includes my mass of the setup, the velocities, and the kinetic energy per trial, and some constants here and there. Rest assured, if you want to look at my data and you think it's bullshit, I'll be putting a link in the description to this Google Sheet so you can check it out. Hopefully, I can do this experiment all in one take so that the environmental factors like temperature or time doesn't affect my experiment. And to that, if you're doing this experiment also, I hope you take that into consideration. With all these details out of the way, we can now begin crashing. So now that our experimentation is done, the first thing that I actually want to look at is if there's any damage to the ducts that we have and if there's any damage to the drone itself. Honestly, I don't think I see any damage to any of the components such as the frame, the flight controller, or the motors. Looking at the electronics such as the camera and the all-in-one, honestly speaking, I don't see any damage. And even at the end of our testing, it was still flying fairly fine. And yeah, that's actually a good thing because I designed Hachidorii to essentially sacrifice the ducts in order to protect the electronics. So I'm happy that that's translating well even when I'm intentionally crashing. Going to the motors, these RCN towers are honestly blowing my mind away. They've been flying great for all these months that I've been using them, and even now, after all that crashing, they're still really smooth. Like, hear this. I can't believe that they're still smooth. So this realization kind of made me think that ducts don't necessarily have to be as rigid as possible to be able to protect the motors and propellers on our drones. There is kind of a threshold that we can have where, despite being at the most flexible or at the most rigid, it will still protect the propellers and motors on our drones during a crash. Moving into the ducts that we've tested, honestly speaking, there's actually not a lot of damage on these ducts. The only thing that is worth noting is the fact that the lightest material that is 3D printed, which is HPPA12, did experience some breakage here at the mounting, where you can see kind of just ripped off over there, which is kind of expected because that's where the thinnest amount of material is. But yeah, I'm surprised that even in all of these testing, only one managed to break at the weakest point. But yeah. After looking at our footage, I wanted to discuss two things that I found out. The first is honestly a really dumb mistake on my end, but it's with regard with how the ducts protect the motors and the propellers. So we're actually going to have two loads for the testing, mainly because it's harder to squeeze something like this than to bend something as a whole like this. This is true because of the nature of 3D prints. They are generally stronger in one axis, which is the axis parallel to the layer lines. This is also true because of the geometry of the duct, where a line is easier to flex, like up and down, than a circle being squished or stretched. Because it's harder to actually bend, you can make the ducts less actually rigid without getting too many disadvantages in protection. And we can make the ducts less actually stiff through a change in material and or a change in geometry. I even found out that the axial axis of the ducts don't even absorb that much energy as the rest of the drone still moves forward after the impact. And I'll actually call this the initial impact because there is generally a second less severe impact where either the canopy or the back ducts hit the board. You can say that in some ways, the total kinetic energy of the drone moving forward is equal to the initial impact's energy plus the secondary impact's energy. And all this basically means that the initial impact's energy was less than we initially thought of. Now, the second thing that I want to talk about could somewhat give an idea of the durability of the ducts. Now, I know there's other things to consider like material properties, sprint settings, blah 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 blah, but based on the footage that I got, I found a phenomenon that could be related to the stiffness of the ducts, which I will call wobbling. Now, the technical term for this in engineering is called simple harmonic motion if you want to look more into this, but I'll just try to make it simple. Wobbling is the process where after the second impact, the ducts start oscillating tangentially or up and down. Now, the part that I found really cool was the fact that the stiffer materials had minimal to no wobbling. Materials like ABS, ASA, and PLA. On the other hand, with the exception of the Mobula 7 V2 ducts, which I don't know, maybe I just didn't test it properly, the more flexible materials like PETG and HPPA12 had lots of wobbling. Now the question is wobbling good? Well, the question isn't necessarily easy to answer, but we can simplify ducts as springs. The more rigid ducts act like stiffer springs, while the flexible ducts act like springy springs. Who wrote the script? While the flexible ducts can release energy from the impact through wobbling, the stiffer materials transfer that energy throughout its entire body. And this is actually why, for those of you who have broken your V2 ducts, you can see the break occurring at the thinner sections of the duct that is close to the middle. I guess in simpler terms, ducts that are rigid absorb the energy from the crash, but since there's no way of releasing that excess energy, like through wobbling, it then just releases energy by putting stress at a certain point until that point breaks as it experiences more crashes. Whew, that's a lot of discussing. Since I know this video has been kind of confusing or maybe too technical, let's just have a quick summary of what we've discussed so far. First, we found out that our ducts don't have to be that actually rigid for two reasons. A, ducts are stronger actually, so it probably can easily handle force going in that axis. And B, the drone generally experiences two impacts, which means that the initial impact doesn't actually experience the full kinetic energy of the drone, which is a good thing. Now, with this in mind, it makes sense to go for the more flexible options such as PETG, HPPA12, and the Mobula 7 V2 ducts. However, despite my second point, I honestly will still recommend materials such as ABS and ASA, as I think we can sacrifice rigidity and make them more flexible by changing their geometry, which ultimately will make them even lighter. Which again is a good thing and is also something that we can do for the heavier materials like polycarbonate and PLA. So yeah, with the question of which material is the best for ducts, I'm leaving it open-ended to you guys. Honestly, there are so many different materials out there now and different variants of different materials, and kind of just a lot of things to consider still, like affordability, places you can find them, and just being able to print these things in general. So in some ways, if you want just a straightforward answer, ABS and ASA pretty good. PETG, surprisingly fine alongside polycarbonate. And PLA, if you could get like a more flexible or less heavy version, will probably also be a good material for ducts. Whew, oh my goodness, that was a lot of talking and yapping. But if you've reached this part of the video, I want to say congratulations! But also thank you for watching part 2 of my material testing for 3D printed ducts. I know it was kind of confusing or too technical or maybe a lot of yapping, but honestly it was really eye-opening and can honestly be a good stepping stone in seeing the potential of 3D printed ducts for these tiny whoops. I'm generally excited to see how you guys interpret this information, and honestly, I'm more excited to see what kinds of ducts our little community comes up with, as I think duct geometry is now the next thing that we can experiment with. Wink wink. Wait, I just realized you can't see me wink. I'd also like to give thanks again to PCBWay for honestly making my testing possible. I love experimenting with these things and tinkering and making all sorts of contraptions, and this is something that PCBWay aligns with. They support other innovators and thinkers, and I honestly think that's a great thing. And they don't just do this just by providing manufacturing capabilities, but also from the events that they hold, like their Christmas and New Year promotion. Not only are there discounts, special sales, lucky draws, and even promo codes to look out for, but there's also a holiday themed design event that I think some of you who like to tinker will greatly appreciate. As always, links are in the description if you guys want to check it out. As always, thank you guys for watching my videos and for supporting my channel. I can't believe that we've managed to grow this channel so much in just 1 year, and honestly, I still can't believe that we reached 1K subs. Like, seriously, thank you guys so much. And for like the 4th time now, thank you for watching my videos, and I hope you guys enjoy your holidays and the new year. Cheers to 2025, let's make it a great one. I swear, this is my favorite clip out of all of them. This is the PLA take number 3, and I just think it's comically bing. it just moves. Like there's no second bounce even. Look. Doink. It's so stupid. It's just cartoonishly. Look, I'm gonna do it manually. It looks so funny. Doink. It doesn't even flex at all. It doesn't flex. It's so funny.